Awesome. Thanks so much, everyone, for braving the Friday morning wake up and coming to the session. So I'll tell you a story that I hope really everyone will be able to follow basically every slide, because it'll be a little bit different than many of the talks that you've already heard in the conference. And indeed, it'll be a story about high pressure physics and how to make interesting measurements and imaging under high pressure. So today's story is a little bit different than many of the 2D stories that you're hearing, because there will not be a 2D material. But I'd like to hopefully convince you that the techniques that we've been developing in my group are broadly applicable, and I do hope that many of you will come chat with me in the breaks and at lunch. And it'd be very interesting to think about what types of questions one could answer with the types of techniques that my group has been developing. So pressure is actually typically one of the classic tuning parameters. If you remember undergraduate statistical mechanics, you naturally think about the pressure, temperature, phase diagram, or pressure volume as tuning parameters. And indeed, whether it's solids, liquids, or gases, all of them have different types of behavior under pressure. So in the context of quantum materials, we often think about pressure as being able to change phases of matter, whether it's via structural phase transitions or other types of ordering. But we also think about pressure as being able to stabilize new phases of matter. So hopefully I get there, but if not, please ask me. One of the topics that my group has been exploring is a rather controversial, albeit somewhat interesting topic, which is pressure-stabilized superconductivity in the hydride materials. So hopefully I'll get to a little bit of that. Good, so most of the story will be about introducing the general technique and sort of conceptually how we look at things under pressure. Just as a quick funny story, in my undergraduate physics class at Harvard, I had a student present to me, offer a class presentation. I said, broadly, the presentation should be about how pressure can change the shape and tune materials. And his talk started off with this type of an apparatus. So indeed, one can apply pressures using large types of pistons and cylinders, but one should also remember, specifically in the context of 2D materials, that pressure is force over area. So the actual tool that we'll be using today and we'll be discussing is an apparatus designed by Bridgman in the early 20th century, and it's called the diamond anvil cell. So I know that most of you don't work on high pressure science, so I'll be very, very slow and introduce this. So the diamond anvil cell is very simple. The idea of applying high pressures is to put some sample in between something that can apply large forces, in this case diamond anvils, and does so over small areas so that we can get large pressures. So the basic operating schematic for a diamond anvil cell is extremely simple. We have a backing plate that basically holds the entire apparatus in equilibrium. We have two diamond anvils, which are almost sort of gem-cut diamonds, faceted diamonds that have their surface laser cut so that we have a flat surface that allows us to apply pressure. The two anvils here, then you can see, naturally define something like a sample chamber inside of them. Inside that sample chamber, typically one puts whatever samples one's interested in, but also one puts a little chunk of ruby, and that's because ruby acts as a pressure calibrant. So the photoluminescence of ruby is extremely well calibrated under pressure, so most oftentimes in many of these experiments you'll see a little chunk of ruby. You know that if you stuck a piece of Play-Doh between two anvils and you squeezed, or a material in general, it would typically expand out the sides. So to prevent that from happening, we have, this is a cross-sectional view, you have a little bit of an O-ring that surrounds the sample chamber to make sure that the sample doesn't actually get squeezed out of the sides. And in addition to the inside the sample chamber defined by that O-ring, typically you have either a gas or a liquid pressure medium to try to make the pressure and redistribute it as hydrostatically, as spherically symmetrically as possible. So that's the basic setup that we're working with to apply high pressures in quantum material systems. And these types of systems can reach quite large pressures. So typically atmospheric pressure is about 1 to 1,000 pascals, and diamond anvil cells can reach hundreds of gigapascals, so many, many orders of magnitude larger. I would say typically for most condensed matter experiments, people are typically tuning things between, up to around 10 GPa or maybe even a little bit less than that. Although for the hydride superconductors that I may get to, those are going to be at the megabar regime, so hundreds of gigapascals. Good. So what types of measurements are certainly you guys familiar with working on, but is also typical to explore inside these anvil cells? Well, one certainly does diffraction type things, looks at X-ray diffraction, can we do scattering experiments, we can work at beamlines, but perhaps the more common tabletop measurements that one typically does, certainly in my group that one does, is one tries to make measurements of electrical transport and see how those measurements change as a function of pressure, and one also tries to make measurements of magnetic fields under pressure. And so electrical transport needs no introduction. I can just tell you that the way you do magnetic measurements for these diamond anvil cell experiments is also super simple. You think about sort of a pickup coil design. So you imagine having a solenoid that basically applies a little bit of an AC current that applies a magnetic field, and then you lock into that response and try to measure in a pickup coil the changing magnetic response of your system. So one thing you can kind of immediately see about this type of a geometry in terms of measuring magnetic fields of samples at high pressures is the challenge that I'd like to emphasize, which is that it's very, very tough to make local measurements inside a diamond anvil cell. I'm giving specifically the example of magnetism, but this is true more generally. So indeed, it's hard to imagine sticking a magnetometer, whether it's one thing, for example, Patrick Malatinsky and Vincent Jacques earlier in the week gave beautiful talks about using scanning tips or using defects in HBN to sense things. But it's quite difficult to imagine how I would stick a scanning tip into the high pressure chamber to be able to actually make local measurements of magnetism at the sample. So one of the enduring challenges, something that I kind of became accustomed to from talking to my collaborators, is that it's very difficult to image or measure local properties, for example, magnetism of materials under pressure. So today's talk very broadly will introduce just a super simple strategy. Again, I hope everyone will follow very clearly. And the idea is to try to develop a technique to be able to image magnetism in situ, so directly inside the high pressure chamber at high pressures while one is applying pressure to the material of interest. So I can already immediately introduce the strategy. It's kind of such an obvious strategy that I think with a little bit of thought, many of you would have come up with this. The strategy is, it would be very useful if one could somehow embed an extremely thin layer of sensors directly inside the apparatus that is applying the pressure. It turns out you will already suspect from, I hope, earlier talks that you heard in the conference what this particular sensor is going to be, but the idea in my talk is to try to embed maybe a shallow layer of an ensemble of, in this case, magnetic sensors, maybe about 50 nanometers or 100 nanometers below the surface of the diamond anvil that's actually applying the pressure. And then the super simple idea is to do, for example, confocal microscopy, assuming that one can transduce the magnetic signal that's measured by these sensors into an optical signal. Then one can do confocal microscopy through relatively transparent diamond and be able to image what exactly is the magnetic field measured by these sensors locally. And because they themselves are close to the sample, one then gets to make local pictures, take images of magnetism inside the sample chamber as one is applying pressure. So a very, very simple idea. As a very quick aside, I'll quickly introduce what the sensor is. There'll be 2 slides on this, but if we don't follow these 2 slides, at some level, it's just a spin 1 magnetic dipole. And that magnetic dipole is the thing that we're going to look at. We're going to be doing Zeeman spectroscopy on that dipole to look at local fields. So the sensor is something that, again, you've heard about a little bit earlier in the week. In particular, it is a nitrogen vacancy center. So this immediately connects to diamond anvil cells. NV centers are a particular type of defect inside diamond lattices, which correspond to a substitutional impurity of nitrogen adjacent to a vacant lattice site. And just in case there's someone who works on pressure, the way we make these NV centers inside the anvils is we take type 1b anvils and we do ion implantation of carbon to be able to generate vacancies, and then we anneal to generate NV centers. So we're always looking at ensemble measurements. So at some simple level, the resolution, the spatial resolution of our measurements is always going to be something limited by about the diffraction limit. So it's maybe about half a micron or so. Good. So again, at the risk of telling you guys something you already know, but maybe just to make sure that everyone's on the same page, we can ask a very, very simple question. The goal that I said for the talk is to introduce a very simple strategy for measuring local magnetic fields at high pressures. And we should ask ourselves, what exactly is the signal that we typically expect to see coming from one of these NV centers? In some sense, the signal is just about as simple as you can imagine. We're simply looking, if we're interested in DC magnetic fields, at trying to do some spectroscopy of the Zeeman splitting of this magnetic dipole. The lucky thing about the NV center, again, which you might have heard about, is that the fluorescence of the spin sublevels of the NV centers is different from one another. And this allows one to do something called optically detected magnetic resonance. It is just like EPR or NMR magnetic resonance, except we detect the signal not using a loop, but rather using optics, just looking at changes in the photoluminescence. Good. So the signals that you'll see in this talk are actually extremely simple. As I mentioned, it's a spin 1 dipole. So at 0 magnetic field, the transition between the m sub s equals 0 to plus minus 1 states of the spin 1 dipole are degenerate and happen at a particular microwave frequency, about 2.87 gigahertz. And as a function of an increasing magnetic field, there's a Zeeman splitting of the plus and minus 1 states, proportional to basically the Bohr magneton. And that splitting immediately allows you to measure, to back out the projection of the magnetic field along the nitrogen vacancy axis. It turns out that the signals that we'll typically see in an actual experiment look like this. So these are magnetic resonance lines, but instead of the pair of magnetic resonance lines that I showed in the previous slide, you end up seeing 8 different magnetic resonance lines. This can be easily understood, not surprising at all. Diamond has tetrahedral symmetry, which means that you can have the nitrogen vacancy axis along any of 4 directions that's shown here. And because you're most sensitive to the projection of the magnetic field along that NV axis, if you have an ensemble of NV centers all with different orientations and a generic magnetic field that doesn't point along one of them, you will have 8 different Zeemans, or 4 different Zeeman splittings corresponding to 8 different magnetic resonance lines. So from these 8 different magnetic resonance lines, you don't just get a magnitude of the magnetic field, actually you immediately get a vector magnetic field, so you get an orientation of the magnetic field and a local spot as well. Good. So with this notion of the signal clear, I just want to do a little bit of benchmarking before I actually get into a super quick story on the hydrides. This will be a material that all of you are familiar with. I don't know if the layered ones I think people are still interested in, but we're looking at bulk bisco, a classic superconductor. It superconducts without pressure, but I'm putting it under pressure just to demonstrate the technique. I believe TC does change a little bit under pressure, but I don't think it actually goes up. So the geometry of the setup is extremely simple, so you can kind of see sort of this is an optical sort of a white light image on the sample chamber, and you can see that the sample of bisco is about 50 microns or so, maybe a little bit smaller, a little bit bigger. There are a couple of pieces of ruby here, as I mentioned, that we use to calibrate, and there's actually a microwave wire that you can see obstructing the optical view, and that microwave wire is important because we're going to be doing magnetic resonance spectroscopy, so we need to be able to microwaves to be able to change the population. So that's the basic geometry. So you can see that the sample is sort of stuck on top of the diamond anvil. We sort of apply leads to this by sort of pushing the sample into the leads to be able to do transport at the same time. So the basic set of measurements that my group does on all of these systems is a combination of transport and local magnetic field imaging. I'll focus on the magnetism because that's the thing that's new. So just to give you a little bit of a very, very quick reminder about what one should expect in the system. Bisco is a classic superconductor, and the magnetic signature of a superconductor is the Meissner effect, that one should expel magnetic field lines if one has superconductivity. You all know this, but let me just emphasize what one should see in the types of measurements that we're doing. You have a sample, and you have a layer of magnetic field sensors directly above the sample. So when you apply an external magnetic field, if the sample's in the normal state, in a metallic state, for example, or an insulator, you imagine that the NV centers, the sensors, should just sense exactly a spatially uniform magnetic field that's the same magnitude as what you apply. If you now have a sample in the sample chamber that undergoes a transition to superconductivity and the Meissner effect, the expectation is also kind of simple. So for sensors that are directly above the sample, you should see a reduction in the magnetic field because of this expulsion of the field lines. But the number of field lines is conserved. You can't change that. So that means that actually at the edge of the sample, you should actually see an enhancement of field lines. Okay? And seeing this, is already been done, at without pressures, but really under pressure, it's quite difficult to be able to imagine how to do this. So just to give a little bit of a quick sense of what the raw signal looks like. So here's 2 different points on a sample. It's actually not the same BISCO sample, but doesn't matter too much. And as promised, as a function of increasing magnetic field, so the curves get darker and darker for an increasing value of the applied magnetic field Hz, you see that the Zeeman lines, the splitting between the plus and minus 1 states, gets larger and larger and larger. And in different regions, it may get larger and smaller in different ways. So the typical thing that one does is if one is far away from the sample, one can certainly calibrate the strength of the external field that one applies. And if one's far away from the sample and one looks at a single confocal spot, you can measure what is the magnetic field measured by the NV centers relative to the magnetic field applied by the solenoid. So the applied magnetic field, its Hz, is always H on the x-axis, and the magnetic field measured by the NV via Zeeman splitting is Bz. And if you're far away from the sample, you actually get essentially a line that's literally y equals x. So it tells you that the magnetic field that the NV center measures is exactly the same as the magnetic field that you're applying. But actually, at different points, and we'll be able to say why this is in a second, at different points you can actually see that the magnetic field measured by the NV center is smaller than the external magnetic field. So perhaps from a magnetism perspective, the simplest figure of merit that one can imagine is just defining a suppression factor. So relative to the magnetic field, to the slope being 1, what is the slope of the magnetic field measured by the NV relative to the magnetic field applied on the sample? Okay? So that'll be some number that could be greater than 1 if there's enhancement, or less than 1 if there's suppression. So here's exactly this type of measurement, but now shown in a wide field microscopy image. So this is microns on both the X and Y scale. The sample somewhere hiding here, but this is at high temperatures above the transition temperature of BISCO. It's not an optical image in any ways. All I'm plotting here is the magnetic field measured by NV centers divided by the applied field. This kind of a greenish color is about 1. So aside from rubies, which you can kind of see here mess up the measurement a little bit, you basically see no evidence of the sample. But if you lower the temperature to just below the transition temperature, if you lower the temperature to just below the transition temperature, you start to see something kind of, in my opinion, quite beautiful emerge. So you see that for NV centers that are above the sample, there is a suppression of the magnetic field relative to the applied magnetic field. But the other cool thing is that for NVs that are on the edge of the sample, you see an enhancement of the magnetic field exactly coming from the fact that the magnetic field lines, the number of them has to be conserved. And there's just a super cool feature, not an important feature, but if you look at the sample and you look at transport, you could never say something about there being a break in the sample or any structural infidelity in the sample. But I can promise you that the sample, even though it's a chunk of BISCO, for some reason has a little bit of a cut in its superconductivity. Again, if you average over transport, you still see superconductivity, but here you can kind of see that there is local structure that you can image at high pressures, which would otherwise be quite hard to do. Okay, 1 minute. So so this is what happens as you decrease temperature further. You see that you get even more suppression. And maybe just, I think I won't be able to get through this, but just to pique your interest in a field that probably many of you know as rather controversial and as a terrifying one to work in. We've recently been exploring superconductivity in superhydrides, and as many of you know, there are these hydrogen-based materials where kind of simple BCS predictions already tell you that because of the low mass of hydrogen, you should get a very high pi temperature, and thus relatively high temperature superconductivity. And there's any number of papers that have been reported in the last couple of years. I should say the field is not without controversy. Even some of these plots have already, they're papers that have been retracted. And so my group has been working on a particular material, cerium hydride, and actually doing a combination of transport as well as local magnetic field imaging to understand where exactly in the sample chamber one is seeing superconductivity. We see lots of nice things, evidence of flux trapping. We see the ability to expel magnetic fields on field cooling and zero field cooling. Okay, so with that, I think I'm already a little bit over time, so I apologize. Let me just mention that we also have some very recent measurements on bulk nicolates using the same technique, these bulk nicolates that only superconduct under high pressure. And I should just quickly end by thanking the people who did the work and you for your attention.
Thank you for the great talk, beautiful result. I'm sure there are questions. Yes.
Norm, beautiful data indeed. So what do you find in the latest results on hydrides?
So it's interesting. So the hydrides themselves, you'll probably know, the way that people make the hydrides, just a quick introduction, is it's usually some rare earth metal and a lot of hydrogen. And the way people make these is that they're not stable at ambient pressures, so you have to go to high pressure to be able to make them in the first place, and then you do laser heating. And one of the common problems that people have is just that, in fact, the samples that people have, people assume that they're homogeneous, but actually, even if you look at superconductivity signatures, some look good, some look bad, some look like a drop to near zero, some look like a drop to some other value. And people have made statements about are these type 1, are these type 2, by just assuming that the full area that one laser heats is the hydride sample, and we can very clearly see that it's extremely disordered and granular. So you get, maybe 10 micron-ish size grains of superconductivity. I'm 100%, I'm very, very sure that there is superconductivity in cerium hydride, the one we measured, and probably a lot of the other ones, lanthanum hydride, that we're certainly starting to measure. We tried at some point to work with Ranga on some of his samples, and there we did not see a signal, but I think we probably know why that is now.
Marcus?
Yeah. Sorry, very quick question, very nice talk. Why is Ruby messing up your magnetic field imaging? Is it from the PL?
Sorry, can you say it one more time?
Why is the Ruby messing up your magnetic field?
Yeah, that's super good. It's strain, actually. So the NV center not only sees magnetic fields, but actually there's also strain effects. So its local strain environment differs. And if the Ruby causes a little bit of a different strain environment, then actually you measure that also as a change in the splittings of the NV center. Super good.
Yeah, great work, thanks. Have you, or could you, or have you thought about doing the hydrogen sulfide experiment again, which wasn't as controversial as far as I understand? They had this fairly confident 200 Kelvin.
So we're tackling one controversy at a time. It's not super easy to get funding for these things. AtoCube. We're actually the two that I would say are kind of indeed the big ones are hydrogen sulfide, where there's some nascent controversy, and lanthanum hydride, where I think there's a little bit less controversy, but it is the highest temperature superconductor under pressure. So we're actually starting to tackle lanthanum hydride with the hope of eventually playing with hydrogen sulfide as well.